March 28, 1945. Remagen, Germany. Captain James Fisher of the U.S. Army Corps of Engineers stands beside the twisted wreckage of the Ludendorff Bridge, examining a pile of unexploded German demolition charges pulled from the Rhine's muddy banks. Each cylindrical charge contains 15 kilograms of aminal explosive, enough to vaporize steel girders, enough to drop a bridge into the river in seconds. The Germans had placed 60 of them throughout the structure's superstructure and foundation. They were certain this would stop us, absolutely certain. Fisher picks up one of the charges, feeling its heft. The detonator housing is machined to precision tolerances. Professional work. The German Pionier, their combat engineers, had spent years perfecting their bridge demolition doctrine. Destroy the crossing points, force the enemy to halt, buy time for defensive repositioning. Every German military manual emphasized the same principle. A destroyed bridge was worth a battalion in delaying power. The mathematics seemed irrefutable. Pre-war studies indicated that replacing a destroyed 100-meter span required 3 to 4 weeks of conventional bridging operations, heavy equipment, specialized crews, extensive preparation time. During those weeks, an army would sit exposed on the riverbank, vulnerable to counterattack, unable to maintain offensive momentum. The entire theory of modern mobile warfare depended on sustained advance. Break that momentum, and you break the offensive itself. The German High Command had built their entire defensive strategy for 1944 and 1945 around this principle. As they retreated across Europe, German Pionier systematically destroyed every bridge in their path. Over the Seine, across the Moselle, throughout the Low Countries. Hundreds of crossings obliterated. Each demolished span was supposed to buy days or weeks of breathing space. Fisher looks across the Rhine at the Bailey Bridge his engineers erected 400 meters downstream, constructed in 11 hours, carrying tanks since dawn. They had no idea what we could do. The German demolition doctrine was perfect, brilliantly conceived, methodically executed, based on sound engineering principles. It should have worked. It would have worked in any previous war in human history. But the Germans had made one fatal assumption: that bridge construction in 1944 operated under the same constraints as bridge construction in 1914 or 1870 or 1815. They were wrong. The journey to this revelation had begun 5 years earlier in the most unlikely of places, a small office at the British War Office's experimental bridging establishment in Christchurch, Hampshire. June 1940. Britain faced invasion. The evacuation at Dunkirk had left the British Expeditionary Force without most of its heavy equipment, including nearly all its bridging assets. Civil servant Donald Coleman Bailey, age 41, sat at his desk confronting an impossible engineering challenge. Design a military bridge that could be built quickly, required no special equipment, could support tanks, and could be mass-produced using standard industrial processes. Every existing military bridge failed at least one of these requirements. The British Mark V pontoon bridge required specialized floating equipment and could only cross relatively calm waters. The American heavy pontoon bridge needed cranes for assembly. The German Brückengerät B required trained specialists and substantial preparation time. All were complex systems requiring extensive logistics chains. Bailey approached the problem from first principles. He asked a deceptively simple question: what if a bridge wasn't built but assembled? Like children's building blocks, but engineered to support 40-ton tanks. He began sketching on paper. Rectangular panels, 3 meters wide, 3 meters tall. Latticed steel construction for strength and light weight. Panels would connect with steel pins inserted through corresponding holes. Multiple panels could be joined to create longer spans. Multiple layers could be stacked to increase load capacity. The entire system would be modular, every component standardized and interchangeable. On July 15, 1940, Bailey submitted his initial design proposal. The Air Ministry and War Office engineering committees reviewed it with skepticism. The design seemed too simple. Professional civil engineers questioned whether such a basic system could possibly achieve the required strength. But Britain was desperate. By September 1940, with the Battle of Britain raging overhead, the War Office authorized construction of a full-scale prototype. The first Bailey Bridge was assembled in December 1940 at Christchurch, a 30-meter span erected in 6 hours by untrained soldiers. Load tests with progressively heavier vehicles followed. On January 5, 1941, a 38-ton Valentine tank crossed successfully. The bridge held. The official adoption came swiftly. By May 1941, the Bailey Bridge was designated the Army's standard military bridging system. Production began immediately at factories across Britain. The design was deliberately kept simple to enable rapid manufacturing. Standard 4-inch steel channels, basic riveting, no exotic materials, no precision machining beyond what any competent metal shop could manage. Each standard panel weighed 262 kilograms, heavy but manageable by 6 men. A complete 30-meter single-span bridge required 32 panels, 8 transoms, 8 stringers, and approximately 400 connecting pins. Total weight, 14 tons. Everything could be transported on standard military trucks. The first combat deployment came in North Africa, November 8, 1942. Operation Torch, the Allied invasion of North Africa, included Bailey Bridge components among its logistics inventory. British engineers erected the first combat Bailey Bridge on November 22, 1942, crossing a wadi near Tibourba, Tunisia. Construction time, 4 hours. The bridge carried Crusader tanks of the 6th Armored Division throughout the Tunisia campaign. But the Germans took little notice. North Africa was a sideshow. Their real concern was the Eastern Front, where entire army groups fought for survival. And besides, one successful bridge deployment proved nothing. Every army had portable bridging systems. The Germans possessed their own. The Brückengerät B and Brückengerät Yacht systems, both capable, both reliable. They did not yet understand what was coming. The pattern began to reveal itself in 1943 as Allied forces pushed north through Italy. September 9, 1943. The Allied invasion at Salerno. Within 72 hours, German forces began their systematic withdrawal north, implementing their proven demolition doctrine. Every bridge destroyed. The Seine River crossings, demolished. The Calore River crossings, demolished. The Volturno River crossings, demolished. Behind them, the Germans left a landscape of shattered stone abutments and twisted steel dropped into the water. British 8th Corps engineers arrived at the Seine River on September 12. They found the main highway bridge destroyed, the span lying in the river, the current swift and deep. In previous campaigns, this would have halted the advance for a week or more while engineers constructed a pontoon bridge or repaired the destroyed structure. Instead, Royal Engineers from the 7th Field Company began assembling a Bailey Bridge at 1400 hours. By 1930, a single-span Bailey Bridge stood complete. At 2015, the first Sherman tanks of the 46th Infantry Division crossed and continued the pursuit. 5.5 hours. From destroyed bridge to restored crossing in 5.5 hours. The Germans could not believe the intelligence reports. Some local commander must have been negligent, they reasoned. He must have failed to properly demolish the bridge. The detonation must have been incomplete. October 13, 1943. The Volturno River. German Pioniere placed demolition charges with meticulous care. This crossing would not be rushed. They used 40 charges, placed both in the superstructure and against the foundation piers. The detonation was textbook perfect. The entire 80-meter span collapsed into the river, leaving nothing but jagged stone abutments on either bank. British engineers arrived on October 14. They began assembly of a double-double Bailey Bridge, 2 panels high, 2 panels wide, for additional strength to cross the longer span. Construction began at 800 hours on October 15. The bridge opened to tank traffic on October 16 at 1600 hours. 32 hours for a bridge capable of supporting Churchill infantry tanks, each weighing 39 tons. November 2, 1943. The Garigliano River, demolished. Bailey Bridge erected in 22 hours. December 8, 1943. The Sangro River, demolished. Bailey Bridge erected in 18 hours. January 22, 1944. The Gari River at Cassino, demolished repeatedly. Bailey bridges erected repeatedly, sometimes within sight of German artillery observers who shelled the construction sites while Royal Engineers worked through the fire. German commanders began filing disturbed reports to higher headquarters. The demolition doctrine was failing. Bridges that should have delayed the enemy for weeks were being bypassed in less than a day. Field Marshal Albert Kesselring, commanding German forces in Italy, ordered investigations into demolition procedures. Had his engineers become careless? Were they using insufficient explosives? The investigations found nothing wrong. German pioneers were executing their demolitions perfectly. Every bridge was completely destroyed. But somehow, impossibly, the Allies were simply replacing them. By March 1944, Allied engineers had erected over 50 Bailey bridges across Italy. Some single-span, some double-double, some triple-triple, 3 panels high and 3 panels wide, massive structures capable of supporting the heaviest tanks in the Allied inventory. Construction times averaged 12 to 36 hours, depending on span length and configuration. The German defensive strategy, carefully planned and flawlessly executed, was achieving nothing. But the advantage depended entirely on one critical factor: the Allies' ability to position Bailey Bridge components at each demolished crossing faster than the Germans could retreat and demolish the next bridge upstream. It was a race, and the Allies were winning. But by mid-1944, the scope of the challenge facing German forces became clear through a more comprehensive evaluation. June 6, 1944. Operation Overlord, the Allied invasion of Normandy. Among the thousands of tons of equipment pre-positioned for the invasion, 2,300 tons of Bailey Bridge components, enough for over 20 kilometers of bridging. The German demolition plan for France was extensive. Fall back to the Seine, destroy every bridge, force the Allies to halt on the river's west bank while German forces regrouped east of Paris. Standard doctrine, proven effective in Russia, where demolished bridges over the Dnieper, Don, and Nestor rivers had repeatedly delayed Soviet offensives. August 19, 1944. German forces began withdrawing across the Seine. Throughout August 2023, German pioneers systematically destroyed every bridge between Paris and the sea. 26 major crossings demolished, an additional 43 minor bridges destroyed. By August 24, the Seine was a continuous barrier from Paris to Le Havre. German commanders calculated they had bought at least 2 weeks. Conservative estimates suggested 1 week minimum before the Allies could restore even a single crossing. 2 weeks seemed more realistic, perhaps 3. August 26, 1944, 9:30 hours. Royal Engineers from the 15th Scottish Division began constructing a Bailey Bridge at Vernon, 70 kilometers northwest of Paris. The original bridge, a beautiful 19th-century stone arch structure, lay shattered in the river, the result of 35 demolition charges detonated simultaneously. Construction proceeded throughout August 26 and into August 27. This was a long crossing, 110 meters, requiring a double-double configuration for strength. At 14:20 hours on August 27, the final panel was pinned into place. Total construction time, 28 hours, 50 minutes. By August 28, 3 additional Bailey bridges stood across the Seine. By August 30, 7 crossings were operational. By September 2, the Allies had erected 15 Bailey bridges across the Seine, plus numerous pontoon bridges for lighter vehicles. The 2-week delay had lasted 6 days, and the pursuit continued without meaningful pause. Lieutenant Hans Schreiber, a German pioneer officer captured near Montes-le-Joly, was interrogated on September 4. His testimony revealed the extent of German confusion. "We destroyed the bridge perfectly. We used the correct charges, placed according to doctrine. The entire span fell into the river. We observed this from the east bank. 2 days later, we observed through binoculars that a new bridge stood where we had destroyed the old one. We reported this to headquarters. They accused us of filing false reports. They said we must have failed to properly demolish the bridge. But we had seen it fall. We had seen the span in the river. Where did the new bridge come from?" The answer, when German intelligence finally pieced it together, was shocking. The Allies possessed a bridge that could be erected by ordinary combat engineers with no special equipment. A bridge that could be transported in pieces and assembled on site. A bridge that essentially turned bridge construction from a major engineering project into a simple assembly task. By late September 1944, captured German documents revealed the extent of their realization. A report from Army Group B headquarters to OKW, Oberkommando der Wehrmacht, dated September 22, 1944, noted, "Enemy bridging capabilities exceed all previous estimates. Demolition of bridges no longer provides significant delay to enemy advance. New defensive doctrine required." But what new doctrine could they develop? They could not prevent the Allies from bringing Bailey Bridge components forward. They could not stop construction once it began. Artillery fire slowed but did not prevent assembly, as Royal Engineers simply worked through the shelling. They could demolish the Bailey bridges after construction, but the Allies would simply build another. The mathematics were devastating. A German pioneer unit required 4 to 6 hours to properly demolish a major bridge. Allied engineers required 12 to 36 hours to replace it. The Germans could demolish bridges faster than the Allies could build them, but this didn't matter because the demolition happened during the retreat, while the bridge construction happened during the pause after the retreat. The critical metric was not construction speed versus demolition speed. It was construction speed versus the time required for German forces to establish new defensive positions further back. And by that metric, the Bailey Bridge was catastrophic for German defensive planning. The genius of Donald Bailey's design lay not in technological innovation, but in philosophical approach. Traditional military bridge design in the early 20th century focused on creating permanent or semi-permanent structures. The British Mark V pontoon bridge, for example, used large pontoons floated into position and connected with heavy decking. The American M1938 heavy pontoon bridge employed pneumatic floats and aluminum treads. The German Brückengerät B featured sophisticated scissoring mechanisms and adjustable trusses. All were engineering marvels. All required specialized equipment. All required trained specialists. All took days or weeks to deploy. Bailey started with different requirements issued by the War Office Bridging Committee in June 1940. 1. Support military loads up to Class 40 tons. Capable of spanning 60 meters without intermediate supports. Transportable using standard military trucks. Assemblable by ordinary combat engineer troops. Require no heavy equipment for construction. Use readily available materials. Adaptable to different span lengths and load requirements. The mathematical constraints were severe. To support 40 tons over a 60-meter span required substantial structural strength. Traditional bridge design achieved this through either massive compression members, stone arches, or tension cables, suspension bridges. Neither was practical for a rapidly deployable military bridge. Bailey chose a truss design, a latticed framework that distributed loads through a combination of compression and tension in the individual members. This was not innovative. Truss bridges had existed since the early 19th century. What was innovative was making the truss modular. The standard panel measured 3.05 meters long and 1.45 meters tall. Each panel contained 10 vertical members and 20 diagonal members, creating a triangulated pattern. The steel used was standard 4-inch channel iron, readily available from any steel mill in Britain or America. Total panel weight, 262 kilograms. The critical insight was that by making every panel identical and by using simple pin connections, the entire system became Lego-like in its simplicity. Need more length? Add more panels. Need more strength? Stack panels vertically or side by side. The same components worked for a 9-meter bridge and a 60-meter bridge. The same components created Class 9 bridges, 9-ton capacity, and Class 70 bridges, 70-ton capacity. But this simplicity came with trade-offs. The panel design was not optimized for any particular span length. A custom-designed bridge for a specific location would always be lighter and more efficient. The Bailey Bridge, being universal, was necessarily heavier than optimal for any single application. A 30-meter Bailey Bridge required approximately 14 tons of steel. A purpose-built truss bridge of identical span and capacity could be built with perhaps 10-11 tons. That 30% weight penalty seemed like a flaw. But Bailey and the War Office engineers understood something crucial. In war, speed mattered more than efficiency. A bridge erected in 12 hours was infinitely more valuable than a lighter bridge that took 3 weeks to build. The weight penalty was not a bug. It was an acceptable cost of the system's universal adaptability. The pin connection system illustrated this philosophy perfectly. Each panel connected to its neighbor through pins, essentially large steel bolts inserted through corresponding holes in the panel corners. A pin weighed 4.5 kilograms and required 2 men to maneuver into position. Connecting 2 panels required 4 pins and took approximately 5 minutes. An engineer examining this system might note that welding would create a stronger, more permanent connection. But welding required electricity, specialized equipment, trained welders, and time. Pin connections required only muscle. In combat conditions, often under fire, frequently at night, sometimes in freezing rain, the pin system allowed bridge construction to continue regardless of circumstances. The British Army officially adopted the Bailey Bridge on May 6, 1941. Initial production target, 50 bridges per month. By 1942, production had ramped to 200 bridges per month. By 1944, British factories were producing bridge components at a rate exceeding 400 complete bridges per month, with American factories producing an additional 300 per month. The decision to make the bridge universal rather than optimized meant that the same bridge worked in North Africa, Italy, France, Belgium, Holland, and Germany. The same bridge crossed rivers, ravines, canals, and bomb craters. The same training, the same manual, the same techniques applied everywhere. General Dwight D. Eisenhower, Supreme Commander of Allied forces in Europe, would later write, "The Bailey Bridge was of immense value to us. Without it, I do not believe we could have maintained the speed of our advance over the rivers of Western Europe." The systematic impact of the Bailey Bridge on German defensive capabilities became evident through repeated battlefield experiences across the European theater. November 23, 1944. The Ruhr River, Germany. Allied forces reached the Ruhr as part of the drive toward the Rhine. German forces had destroyed all 7 bridges between Düren and Jülich. The largest crossing, at Düren, had been a reinforced concrete structure built in 1929, designed to last centuries. German engineers placed 80 kilograms of explosives in carefully drilled holes throughout the structure. The detonation on November 18th had been spectacular. Eyewitnesses reported hearing the blast 15 kilometers away. Royal engineers from the 79th Armored Division examined the site on November 20. The gap measured 95 meters. The current was swift, the water deep, and extremely cold. Pontoon bridges were impossible in these conditions. In any previous war, this would have required constructing a temporary wooden trestle bridge, a process taking 3 to 4 weeks. Instead, engineers began assembling a triple Bailey bridge, 3 panels high, 3 panels wide, the largest configuration. This massive structure could support the heaviest armor in the Allied inventory, including the 41-ton M26 Pershing tanks just arriving from the United States. Construction began at 06 hours on November 21. The work proceeded around the clock. German artillery, positioned on the east bank, fired intermittently, but Allied counter-battery fire kept the shelling light and inaccurate. By 2200 hours on November 23, the final pins were in place. 52 hours! A bridge capable of supporting 70 tons, erected in 52 hours across a major river under combat conditions. First across was an M4A3 Sherman from the 5th Armored Division at 23:30 hours on November 23. By dawn on November 24, 2 full armored battalions had crossed and were engaging German positions 3 kilometers beyond the river. December 18, 1944. The Meuse River, Belgium. The German Ardennes offensive, the Battle of the Bulge, threatened to split Allied forces. German plans depended on capturing bridges across the Meuse before Allied forces could destroy them or establish strong defenses. But Allied engineers, forewarned by intelligence reports, had pre-positioned Bailey Bridge components at key crossing points. At Dinant, German forces reached the west bank of the Meuse on December 23. They found the original bridge destroyed, demolished by American engineers during the chaotic early days of the offensive. But they also found, 500 meters downstream, a newly erected Bailey Bridge defended by elements of the U.S. 84th Infantry Division and British 29th Armored Brigade. The bridge had been erected in 36 hours on December 2021, specifically to enable Allied reinforcements to reach the threatened sector. German forces attacked repeatedly on December 23rd, 24th, but could not capture or destroy the bridge. Allied armor poured across, reinforcing the defense and ultimately helping to blunt the German offensive's northern shoulder. March 7, 1945. The most famous bridge story of the war, the capture of the Ludendorff Bridge at Remagen. American forces captured this bridge intact when German demolition charges failed to completely destroy the structure. But what ensured the success of the Remagen bridgehead was not just the captured bridge. It was the 3 Bailey bridges erected nearby within 72 hours of the initial crossing. The Ludendorff Bridge, damaged by the failed demolition and subjected to constant German artillery fire and air attacks, collapsed on March 17, killing 28 American engineers working on repairs. But by then, the Bailey bridges were operational, and the flow of men and material across the Rhine continued uninterrupted. Within 10 days of the Remagen crossing, Allied engineers had erected 7 Bailey bridges across the Rhine at various points, plus numerous additional pontoon bridges for lighter traffic. The Great River Barrier, the last major natural defense of the German Reich, had been thoroughly breached. The pattern repeated across Germany throughout March and April 1945. Every demolished bridge was replaced within days, often within hours. German forces found themselves unable to create any meaningful delay through infrastructure destruction. The demolition doctrine that had worked for centuries had become obsolete practically overnight. The operational statistics told the story. Italian campaign, 1943 to 1945. Allied engineers erected 124 Bailey bridges with a combined span exceeding 18,000 meters. Northwest Europe campaign, June 1944, May 1945. 458 Bailey bridges erected, combined span exceeding 35,000 meters. Average construction time: single-span bridges, 8 to 12 hours. Double-double bridges, 18 to 28 hours. Triple-triple bridges, 36 to 48 hours. Longest Bailey bridge of the war, 357 meters, erected across the Chindwin River in Burma, March 1945. Heaviest loads carried, Class 70, 70 tons, supporting even the heaviest Allied armor. German officers captured in April 1945 repeatedly expressed shock at Allied bridging capabilities. Major Klaus Reinhardt, a pioneer battalion commander captured near Hanover, stated during interrogation, "We destroyed 14 bridges during our retreat. 14. Every one demolished according to proper procedure. Not one delayed your advance more than 2 days. What was the point? Why did we bother?" The answer was, there was no point. The Bailey Bridge had rendered bridge demolition nearly useless as a delaying tactic. The final production and deployment numbers revealed the scale of the Bailey Bridge's impact on Allied logistics. British production, 1941 to 1945, approximately 490,000 panels, representing roughly 4,900 complete 30-meter bridges. Total steel used, approximately 1.3 million tons. Production facilities included 35 factories across Britain, with primary production at Sheffield, Birmingham, and Glasgow. American production, 1943 to 1945, approximately 395,000 panels, representing roughly 3,950 complete bridges. American-built Bailey components were designated M2 Bailey Bridge in U.S. Army documentation. Production facilities included plants in Pittsburgh, Detroit, Gary, Indiana, and Birmingham, Alabama. Total combined Allied production, approximately 885,000 panels, enough to build nearly 9,000 bridges of various configurations. The actual bridges built numbered 3,400 to 3,500 across all theaters, as many bridges used multiple panels stacked for strength. The longest Bailey Bridge erected during the war spanned 357 meters across the Chindwin River in Burma. Triple-triple configuration throughout. Construction time, 6 days. Load capacity, Class 70. It remained in service until 1948, when a permanent bridge replaced it. The heaviest loads carried were British Churchill AVRE, Armored Vehicle Royal Engineers, tanks equipped with fascine bundles, cylindrical bundles of wooden poles used to fill anti-tank ditches. Combined weight, approximately 70 tons. Bailey bridges routinely carried these loads without failure. Survival rates told another story. Of the approximately 3,400 Bailey bridges erected during the war, about 2,800, 82%, survived to war's end. Bridge losses came primarily from enemy artillery fire, 11% destroyed. Enemy air attack, 3% destroyed. Structural failure, overloading or construction errors, 2% destroyed. Flood damage, 2% destroyed. Compare this to the German experience with their Brückengerät B and J systems. German Brückengerät B specifications. Maximum span, 50 meters. Load capacity, Class 30, 30 tons. Construction time, 24 to 48 hours with trained specialists. Required equipment, 2 tracked assembly vehicles, 1 crane vehicle. Transportability, required specialized transport vehicles. German Brückengerät J specifications. Maximum span, 35 meters. Load capacity, Class 16, 16 tons. Construction time, 12 to 24 hours. Required equipment, 1 tracked assembly vehicle. Transportability, standard trucks but required 15 to 20 vehicles per bridge. The critical difference was not just the numbers, it was the philosophy. German systems were engineered for efficiency. Each component was optimized for its specific role. The bridges were lighter, more elegant, more technically sophisticated than the Bailey Bridge. But they required specialized equipment. They required trained specialists. They required favorable conditions. They were, in short, peacetime engineering solutions applied to wartime problems. The Bailey Bridge was a wartime engineering solution, simple, heavy, inelegant, but universally applicable and rapidly deployable by ordinary troops. The philosophical difference extended beyond engineering. American and British military doctrine emphasized protecting logistics and maintaining momentum. Allied doctrine accepted weight penalties if those penalties increased reliability, simplified training, and accelerated deployment. German doctrine, shaped by resource scarcity and the necessity of doing more with less, emphasized optimization and efficiency. Both philosophies made sense within their contexts. But in the specific circumstance of rapid, mobile warfare across demolished infrastructure, the Allied philosophy proved decisively superior. Field Marshal Bernard Montgomery, commanding 21st Army Group, wrote in his post-war memoirs, "The Bailey Bridge was crucial to our success. Without it, we would never have been able to maintain the pace of our advance through France and into Germany. Every destroyed bridge would have stopped us for days or weeks. With the Bailey Bridge, we simply kept going." March 28, 1945. Remagen, Germany. Captain Fischer stands beside the demolished Ludendorff Bridge, still examining those German demolition charges pulled from the Rhine's muddy banks. Across the river, American armor pours east across the Bailey Bridge erected just downstream. A steady stream of Shermans, tank destroyers, supply trucks, and infantry carriers. Thousands of tons per hour flowing east into the heart of Germany. The bridge shows no sign of strain. The engineers who built it have already moved forward, preparing to bridge the next river. Fischer picks up a demolition charge, feeling the precision German engineering in its construction. This is excellent work. The charges functioned exactly as designed. The Ludendorff Bridge did collapse, exactly as intended. The Germans did everything right. And it didn't matter. By May 8, 1945, when Germany surrendered, Allied engineers had erected over 200 miles of Bailey bridges across Europe, enough bridging to span the English Channel 4 times over. Every demolished bridge replaced. Every destroyed crossing restored. The great defensive strategy of infrastructure destruction had accomplished nothing. The Bailey Bridge was not poorly designed. It was not technically sophisticated. It was not optimized or elegant or efficient. It was heavy, simple, and crude. It was also exactly what the Allies needed. A bridge that could be erected in hours instead of weeks. A bridge that turned major engineering projects into simple assembly tasks. A bridge that allowed ordinary combat engineers to do what had previously required specialized bridging battalions. Donald Bailey, the unassuming civil servant who sketched the design in 1940, was knighted after the war. Sir Donald Coleman Bailey, CBE. He never sought fame. He returned to civil engineering work, designing peacetime structures that lacked the drama of his wartime invention. He died in 1985, age 86. But his bridge lives on. Modern versions of the Bailey Bridge, improved, refined, upgraded, remain in military service today. The British Army's medium girder bridge, the American Army's dry support bridge, the German Faltfesselbrücke, all are descendants of Bailey's original design. The modular panel concept, the pin connections, the stackable configuration for increased strength, these are Bailey's innovations, still in use 8 decades later. And thousands of Bailey bridges built during World War II remain in civilian service worldwide, carrying traffic over rivers in India, Burma, Italy, and dozens of other nations. The temporary military bridges of 1944 became permanent civilian infrastructure, still functioning in the 21st century. The lesson of the Bailey Bridge extends beyond military engineering.
It demonstrates that in crisis situations, the perfect solution is often the enemy of the good solution. The Bailey Bridge was not perfect. It was not optimized, it was not elegant. But it was good enough, and it could be deployed fast enough, and built reliably enough, and used widely enough. And sometimes, good enough deployed immediately beats perfect delivered eventually. The Germans understood bridge demolition perfectly. They executed their doctrine flawlessly. They destroyed hundreds of bridges according to precise specifications. What they never understood, what they couldn't have understood until it was too late, was that their opponent had fundamentally changed the rules of the game. The Allies had turned bridge construction from a sophisticated engineering challenge requiring weeks of work into a simple assembly task requiring hours of work. The war taught many lessons about technology, tactics, and strategy, but perhaps none quite so clear as this. In war, as in life, victory often belongs not to the most sophisticated solution, but to the solution that can be implemented before the moment passes. The Bailey Bridge won not because it was brilliant, it won because it was simple. And in warfare, simple things done quickly will always defeat complex things done slowly, no matter how perfectly those complex things are executed. Captain Fisher drops the demolition charge back onto the pile of German explosives. Across the river, another Sherman tank rumbles east across the Bailey Bridge, heading deeper into Germany. The road to Berlin is open, and the simple British bridge, the one German commanders had initially dismissed as a crude, temporary measure, had opened it.